Good. The stage is yours.
All right. So you heard about Donald and the package manager that he's working on for, or the solver that he's working on for NPM. I'm going to talk about some recent developments that we've done in Spack. I'm going to start with a little introduction of Spack. So Spack is a package manager intended for supercomputers, although you can use it on your laptop or a cloud node or a cluster. It's language agnostic. It's focused originally on build from source and probably still mostly on build from source, but we're starting to get a much more increased focus on using binaries, and particularly using binaries in conjunction with source builds. It allows you to install sort of arbitrarily many versions of any package. And so we allow some divergence of versions. You can have as many versions of one thing installed as you want, but within a process, you have to have one version of any particular package. It's inspired by Nix and Homebrew, and Nix in the sense that we allow all these different versions of things, we hash them. Homebrew in the sense that the DSL looks an awful lot like Homebrew. It's just in Python. And there's thousands of users, I'd say still mostly in the HPC community, and lots of contributors. We care about building across a really wide range of architectures. So like ARM machines, NVIDIA Power 9 machines, different types of GPU machines, and so on. And so we really care about more than just versions when we talk about compatibility. And more than that, we care about different languages. So if you look at the types of things that Spack can build, things like MFEM, this is a finite element library, or LBAN is a neural net sort of training library, Aries is a multiphysics code. These things are, these codes live for tens or more years. And they have a lot of different packages in them, written in different languages. So we care about interop, we care about architecture, we care about ABI, and lots of other constraints at the package compatibility level. So if you look at how Spack works, just at a really high level, if you say that you want to install something, you can provide a lot of constraints that maybe you don't see in other package managers. So just by the default, you might say install MPI leaks. This is a tool for measuring MPI programs. You might specify a particular version. So far, so good. Looks similar. You might also want to specify the particular compiler you want that thing built with, and the particular version of the compiler. You might want a build option for the package. You might want to inject some flags into the build so that these things are built with particular optimization flags. You might want to say that you want to build for a particular microarchitecture, and then you may want to constrain the dependencies as well. So for this, I might want to use mpitch instead of OpenMPI as my MPI implementation. And so you have a lot of customizability over the build with this concise spec syntax that we use. Spack also parameterizes packages. And so unlike a lot of other tools that you might have seen where you have manifests sort of per version of a package, in Spack, there's really just this one recipe. And it's parameterized in the sense that there's kind of two parts to it. Up here, there's sort of there are these directives that define the space of things that you can build. And so for this package, Kripke is a mini app for doing particle transport. This is the web page where you can download it, and we specify a lot of different versions in here with different SHAs. You can download different versions of Kripke. You can build any of them with different variants, and so you can build it with MPI or without MPI. You can build it with OpenMP or without OpenMP. Those are Those are models for parallel computing, and it supports these different sort of ways of parallelizing the code. It depends on a particular library when MPI is enabled, so we can do conditional dependencies. And sort of this says if you set this to true on the command line, then you're going to depend on this package. And it depends on, it has version constraints like other packages. So you can have a dependency on CMake, and you can say I need 3.0 or higher. So with this, this is basically what defines the options you can use with a particular package. And you could build lots of versions of Kripke with this template. The DSL allows declarative specifications of some pretty complicated things that you don't see in other package managers. So like for CUDA, we've added a lot of support for building CUDA packages with all the different options. And so there's a variant for CUDA that you can enable. You can build plus CUDA. This is a mix-in. So like if you write a package and you want to use CUDA, you extend CUDA package, and you inherit these variants from it. And so if you enable CUDA, then there's a whole other variant that is part of the spec when that's enabled. And if you don't enable CUDA, then CUDA Arch doesn't exist. on the spec. We have this sort of telescoping metadata. You have a dependency on the CUDA library when you enable CUDA, and we can restrict the versions based on the values of these features. So this is saying if you want CUDA architecture version 70, then you need CUDA 9.0 or higher. If you want 75, you need 10.0 or higher. And we have a similar syntax for conflicts. So you can say, well, if on x86 64 or any more specific microarchitecture, if I'm building with CUDA at up to 10.2.89, then I have a conflict with GCC at 9 or higher because this version of CUDA doesn't support it. And on PowerPC, it's different. If I'm on PowerPC, it's a different version of CUDA where I don't support GCC 9. And so you can get really specific in here. And we have this very generic conditional syntax. And the way that the solver works in Spack, we call it the concretizer. We take an abstract spec like this, and we generate what we call a normalized graph, where it's partially constrained with all the things we know a priori. We throw that in the concretizer, and it basically fills in all the blanks. And so it does what you would expect from a dependency resolver, but with a whole lot more attributes and a lot more compatibility rules between the packages. And we save that metadata off to disk. We'll talk a little bit about that later. So if you think about this, package solving is more than just SAT. It's more than just satisfying version constraints. It's actually combinatorial search on a pretty large domain with constraints and with optimization. And so you've got a solution space that's a whole bunch of different graphs with different configurations of nodes and edges. You've got versions, dependencies, dependency types, compilers, compiler versions, targets. All of these are node attributes. These are things that are properties of how a particular node was built. And those are subject to validity constraints. So, those version conflicts on GCC, you can't build with certain versions of GCC and certain versions of CUDA. There's things like target and compiler compatibility. We know what versions of GCC can build for, say, Skylake or Cascade Lake. And there's virtual packages and things like that. And once you have this solution space with these constraints, there are a lot of valid solutions, and you want to pick the best one. And so you may want to optimize for things like most recent versions, which we just saw. You may want to optimize for preferred values of different variants, preferred compilers, and you may want to minimize the number of builds in the DAG. And so it's not just one dimension that you're exploring, which is what things like PubGrub do. They start at the most recent versions and sort of explore backwards, and they get optimization as sort of a side effect of that. You're actually doing multi-objective optimization in the solve on this larger space. So there's lots of solutions out there for this. I think a lot of people like to talk about package managers and say that all of this boils down to SAT. And SAT is sort of your lowest common denominator encoding for this type of problem. It's hard to do this stuff with just true and false and to define all the variables. You pretty much have to have a variable per edge, per every attribute in the graph on every component of the model. You have to model some Boolean variable. There are solvers that are much more capable. So there's Z3, which does Satisfiabilty Modulo Theories. You can have a whole lot more interesting semantics in here. And then what we're using here is something called answer set programming. And it's not active server pages. It's answer set programming, which looks a lot like Prolog, but it's a higher level language for SAT is how you could think about it. And it also does multi-criteria optimization, and it can do nice things like produce unsat cores, which are basically like the set of things that are unsatisfiable together to give you better error messages. So just a crash course in ASP. The syntax looks a lot like Prolog. You have terms in your program that look like this. So enable some feature period says enable some feature is true. Node lamps says, hey, there's a node called lamps in your model. Node CUDA says there's a node called CUDA. Variant value lamps CUDA false says the CUDA variant on the lamps package set to false. And depends on lamps CUDA link means I have a dependency from lamps to CUDA, and it's a link dependency. So it's a particular dependency type. And you can express a lot of things with this. There are rules in ASP, and this comes from Prolog again, where essentially you've got a head on the rule, which is what it derives, and you've got a body. This is what if this side of the rule is true, then you derive the thing over here. And so essentially, if you derive node lamps and depends on lamps CUDA link, then you derive node CUDA from this, because both of these things are true. The rule says if anything has a node and it depends on that thing in a particular dependency, then the dependency has to be a node too. So you can read this symbol as if you want to interpret what the program means. Constraints can say what can't happen. So you can do very concise things like disallowing cyclic resolutions by saying, if A depends on B, there's a path from A to B. If A depends on B and B depends on C, or if there's a path from A to B and B depends on C, then there's a path from A to C. So this is just a transitive relationship expressed in 2 lines of code. And if you don't want cycles, then you just say you can't have a path from A to B and a path from B to C. It doesn't exist in the DAG. So that's how you do no cycles. The other interesting thing in ASP that it adds on top of Prolog is something called choice rules. And so this is really what gives the solver freedom to choose things to put in the model. And so let's look at this. This says, if there's a package in the graph, so that's node package, if that's in there, if that, then the solver has to choose, that's this brace notation, exactly one version out of this set in here. And that's the version. And the version has to come from all the possible versions for that package. And so it's pretty expressive. You feed it all the possible versions for the package, and it knows that it has to choose one based on this rule. And so what it does with all this is it searches for things called stable models. And a stable model is a complicated topic that I don't want to get completely into here, but essentially you can think of it as it's a set of all the true atoms or terms in the program that can be deduced from the inputs. It's all of them, where every rule is idempotent. So if you were to apply any rule that's in your program to the set of things that it's derived so far, nothing new would be derived. So you can think of it like a fixed point. It's something that satisfies everything in the program. Unlike Prolog, stable models, which are also called answer sets, they have everything that can be derived. You're not just querying the program and saying, is this true, is this true, is this true? You get a model out that allows you to rebuild your graph afterwards. And the other kind of cool thing, as opposed to Prolog, is that ASP is guaranteed to complete. It won't run forever. It actually will come back eventually. It can be slow because it's NP hard, but it'll come back. So we built a concretizer using this to replace our previous greedy system. And I got to say, it has cleared up a lot of complexity that we had to deal with previously. I could not imagine doing the types of optimizations that we do now without this expressive language to write the solver in. Essentially, all we do now is we generate a bunch of facts that describe the inputs to the program, that describe all the packages and how they can be built. And so typically that's like 15,000 facts right now for a typical package. Includes the dependencies and options, everything you saw in the recipes. And then we combine that with a small logic program. It's like 500 lines of ASP code. And the algorithm is conceptually simpler. We just generate the facts, we throw it in the solver, and we get a model out that has all the facts that we need to rebuild the graph, sort of like the first slide that I showed on ASP. The solve time's a lot faster than what we had before because this is a C++ library. It's not written in pure Python like before. And it can still fall off a cliff, but it seems to do pretty well, and I'll show you how well it does at the end. It makes it very easy to put logic for particular aspects of your solve semantics in one place. So this is the version semantics. This is kind of like what I showed. If you have a node in the graph, you have to pick one version out of all the possible ones. It can't be a conflicting version, and we want to minimize the weight of each of these versions. We assign a weight to them, and that's one way that we can do optimization. Basically, we assign the more recent versions a lighter weight, and we minimize the total weight over the graph to get recent versions. Things like ABI and target logic become pretty simple. So if we know that particular compilers can build for particular targets, and we want to pick the compiler that'll build the best code for us. Previously, we kind of had this sort of chicken and egg problem where we'd have to pick a compiler for a node, and then if we came back and later picked a target, maybe the target wasn't compatible with the compiler, and that's because we were doing the backtracking ourselves or not. And with ASP, you can say something very simple. You can say every node has to have a target, and you basically just disallow the scenarios where the node has a target that the compiler does not support. So you define the full space. There's a little more definition to this than I'm showing here. And then you just rule out the part of the space that doesn't make sense. And you minimize the target weight. And so that basically prefers the more recent targets with things like ABX 512 and so on. So that got a lot simpler. And I showed the CUDA package earlier where we had very general conditions. Basically, like variants can be conditional on other variants. They can be conditional on dependencies. We can have constraints on compilers and so on. we came up with a general way to handle these types of conditions in the solver. And so every condition in the solve now gets an ID, and I'll show what that looks like. So if you wanted to encode something like this, if CMake is at version 3.15 or higher and not using vendored libraries, if it doesn't have the own libs option enabled, then it depends on libarchive version 3.3.3 or higher. What that looks like in our language, in the DSL, is depends on libarchive at 3.3 or higher when this condition is true. So that's not own libs, and this is 3.15.0 or higher. When we convert that to ASP, we generate a condition ID for it, and we associate some requirements with it where they're associated with the ID. So it says, well, if CMake's in the graph, if the version satisfies CMake at this version or higher, and we have sort of separate logic handling these constraints. And if that variant value is set to what we expect, then we impose this other constraint associated with the condition. So we can have a bunch of triggers, and we can have a constraint that gets imposed on something else if these things are true. There's different types of conditions. I'm not going to get into all of them, but essentially we can use this same structure and logic for things like conflicts and virtual packages, providers, dependencies, and so on. It's very general. And the code to trigger that is actually pretty simple. We can say basically, if these condition requirements are true, then there's this colon syntax that we can use to say, put this this term in a rule. So if this condition requirement is true, or any condition requirement that looks like this is true, or any condition requirement that looks like this is true, we basically assemble these rules on the fly out of the inputs. And there's 3 of them because we have different arities for our conditions. If we had conditions with more parameters, we'd have to have another line here. But that's all it is. This is basically the same rule 3 times. And we say if that condition holds, so all of this implies that the condition holds, then we impose the constraints. And then to impose things, basically we say if we're supposed to impose it, and if there's an imposed constraint registered, then we basically turn this sort of encoded imposed constraint into an actual attribute that we then return in our model and build a graph out of. And so if you think about this, it's very general, and we can take some of this and use it for other things. So if you think about the way that packaging systems reuse builds, you might have a graph like this, and most packaging systems that do build caching, they'll take that stuff, they'll resolve the metadata, and they'll hash it. So you'll get hashes per node. These are usually Merkle hashes. And then if you want to say, do I have that binary already, or is it already installed? Is there something already installed that I can build against? You take the hash and you query your cache, and you say, do I have that thing? The problem with this is the hashes are very sensitive. And you may have a bunch of different versions of a package installed that could satisfy the dependencies of the thing that you asked for. It's just that if you're doing hash matching like this, you're not going to find them. And so we wanted to fix that. We wanted people to get much more reuse out of their packages. So what we've done is we can actually use the conditionals that we did before to do this. All we do is we tell the solver about all the installed packages. So we basically say, here's an installed hash. Here's all the constraints that are associated with it. And we basically associate our constraint language with these IDs. And minimizing the builds is actually pretty darn simple. You sort of impose half of one of those generalized conditions. So you say, solver, you can choose a hash for any of the packages. So if a node's in the graph, you can choose at most one hash for that package out of all the installed hashes that we know about. And so that's this stuff over here. These are installed hashes with all their constraints. If you do choose one, then we impose all those constraints when you choose it. So if it enters the model, then all of those other things happen in the solve. And we define a build as just something that we haven't assigned a hash to. And so then we just minimize builds. It's a little more complicated than this, but this is the gist of it. And so using this, basically with these simple definitions and some extra metadata in the solve, we're able to get much better performance out of our solver. So here's before, where we would just say Spack solve, and we're showing what's installed, and we're trying to find HDF5 with a bunch of things installed in a Spack installation. So it comes up, these are all the criteria that we optimize for here. I'm not going to get into the details here, but if it says, oh, I got to build 20 things. And so you can see there that nothing is installed, and the to build number is 20. With this reusing concretizer, essentially it can go and aggressively say, these hashes from what you already have fit the model. they fit the rules that you want to satisfy with. And basically, you get way more reuse out of your installed packages. And so that says 16 packages were acceptable for the solve. All the version constraints and compiler constraints and so on, where they checked out, and we're able to use those in the solve. And so you can see up here that 2build is 4. And the other sort of tricky thing about this that I don't want to get too far into because I don't have a lot of time is that doing this kind of reuse or the minimizing builds at the same time as doing builds themselves, there are different preferences that the users want for these two modes. If you reuse something that you have installed, the user probably installed it a certain way, and you want to reuse it as it is. And so if those things satisfy your constraints, that's fine. But if you end up having to build something, users want things built with the default set the way that they expect from the package. And if you just tell the solver to minimize builds, it's going to turn off variants and do things like give you a CMake without OpenSSL because it just removes a dependency. Some people may want that minimal solve, but in the general case, we try to build the way that we would otherwise without this reuse. And so we don't want the minimization to do weird things to our graph. What we ended up doing is these criteria are not really in order. The installed criteria are lower. The minimizing of builds is sort of in the middle. And all the build criteria are actually higher. And basically, we sum each criterion into 2 buckets, depending on whether it's going to be built or not. And so if something must be built, then its criteria go higher than the minimization of packages. And we adhere to defaults before we try to minimize the number of things that we're building. So we aggressively reuse, but for things that we do have to build, we build them in the usual way. And so that was actually pretty tricky to get right. But it's cool that we can have 16 different objectives for our optimizer and have this degree of control over the graph and also get this kind of reuse. So how does this thing perform? It looks like so far that we can handle pretty large problem sizes with this reusing solver. The setup time doesn't look so good. So this is seconds, and it goes up to like 120 here. Most of these things for a very large repo with like 63,000 packages in it, most of them are getting set up in less than 40 seconds. This is Python data reading and setup of the problem. This is stuff that we can speed up with caching. Over here on the solve side, though, by the time we get into the clingo solver, everything is most everything is less than 10 seconds, which is really cool. So even for a package repo with 63,000 binaries in it, the solver is very fast, or at least it's fast by say Conda solver standards or some other systems like NPM. And 10 seconds is bearable if it saves you several hours of builds. The reason for this is that if you go back here, I'm going to come back here a bit. One of the things that we do is we say, okay, if I pick OpenSSL with this hash, then I'm going to make its dependencies have particular hashes too. And so picking this OpenSSL actually picks all of its dependencies. And what that does is it prevents us from getting the combinatorial blow up that you see with other package managers, where basically anything could be swapped into the DAG. And there's a whole lot more degrees of freedom that cause the solver to go slow. And so here, when you make this decision on OpenSSL, you actually have decided a lot of its dependencies. That's not always what people want. And the next thing that we want to try is we want to see if we can add more optimization criteria to sort of prefer the hashes that things were built with, so that we sort of snap to the built graph, but allow people to diverge from it if they need to. So if they want to swap out a version for one of the packages, we'll stick to the defaults, the things that we know that work, the sort of baseline, is what VC package calls it. But we'll allow you to deviate and sort of try to build it as close as possible to a known baseline that works. And I think we can get similar performance on the solve there because the optimization has this effect of steering the search in a nice way. And so if we know that it's easy to find the sort of preferred configuration and there aren't a lot of other specifications on the solve, it's hard to get the solver wedged in that scenario.
Hey, Todd.
Yep.
You are over time.
Okay. Well, that's all I got. That's my last slide.
If you want to wrap it up in a minute or so, go ahead.
So the longer term view is that we don't want to specify all these constraints manually. Right now, we get all these constraints from a package. And so we have a research project that's looking into doing binary analysis to basically pull out the sort of ABI constraints and actual type information and function information for builds. So we would get rid of some of the human-generated constraints and put compatibility models that take functions into account into the solve. And we want to see if we can have a fast solver that takes all that information into account. And that's way beyond the scope of this talk, but it's something that we're looking at. And I think that the work that we showed here, where we're reusing installed dependencies, enables that. We just have to hang more metadata off those hashes. And so that's it. Thanks.
Awesome. Thanks for the talk, Todd. Very interesting stuff. There's a few questions in the chat, but we don't have time now. So I hope you can sort of jump on over and respond to them.
Yep.
Awesome. Thanks.